Hello and welcome everyone. So after learning different characteristic of damping, critical damping, overdamping and underdamping and the equation of motion in different situations and the measurement of damping which is done by logarithmic decrement, let us do few numericals on these topics. So the first given numerical is that it's a vibrating system consisting of a mass of 5 kg, spring stiffness 120 Newton per meter and a damper with a damping coefficient 5 Newton second per meter. Determine following things: damping factor, natural frequency of damped vibration, logarithmic decrement, a ratio of two successive amplitudes, the number of cycles after which the initial amplitude is reduced to 25%. So let's start. We are given with these data. M value is given, C and K value is given, and we can very easily calculate the critical damping coefficient CC. CC is equal to 2 into root under Km or 2m omega. Okay, so 2 into root under 120 into 5 will give us the value of CC, which is equal to 49 Newton second per meter. Now let us calculate natural frequency. We are given K value and M value both, omega and will be calculated this value. And now damping factor remains very easy to calculate. It's the ratio of C by CC. C is given, CC we have calculated. Let's take a ratio. Rho value is equal to 0.102. Natural damped frequency omega D. Now its natural damped frequency omega D is equal to omega n into root under 1 minus rho square. Omega n we have calculated, rho we have calculated, this value can be very easily calculated. Okay, logarithmic decrement, it is only dependent on the damping ratio, so we can do this logarithmic decrement calculation, which is delta, and it is equal to 2 pi rho divided by root under 1 minus rho square. Let's do it fastly, and logarithmic decrement is 0.64. okay, so ratio between two successive consecutive amplitude, say x1 by x2, okay, and the natural logarithm of this value is equal to delta. Okay, this is clear to us. Now basically we have to calculate x1 by x2 value. Okay, this is what, so we can break this logarithm into this form. With this is e, and e to the power delta will be equal to what? X1 by x2. Okay, this is the formula. Ln ea is equal to b, then a is equal to e to the power b. Okay, this is the formula in logarithm. Okay, now delta value we have calculated, which is equal to 0.64, and we can raise it to the exponent factor. E is equal to 2.73, and you can do it in your calculators. Okay, so x1 by x2 can be obtained as 1.896. now this is a constant. Okay, this can be for any successive amplitudes. Okay, it can be equal to x n by xn plus 1 also, no problem. Okay, now we have to calculate the number of cycle after which amplitude is reduced to 25%. Let's say if x1 was our initial amplitude, then after n cycles what happens? It becomes xn, and x1 is equal to x1 by 4. So amplitude has reduced to 25%. So what we have learned that x1 by xn, if we take log of this, it is equal to n times delta. Okay, very simple formula, because we are taking ratio between not successive amplitude, we are taking ratio between first amplitude and nth amplitude. So it is n times logarithmic decrement has happened. Okay, so this is very simple, and we can do this. N is equal to what? 1 by delta into ln of x1 by xn, and delta we have calculated, delta is equal to 0.64, and xn is equal to what? Xn is equal to x1 by 4. Okay, so this we can calculate, and it will come out as this value, and then we can calculate. It is coming as 2.166 cycles. See, cycles are always in whole number, so we have to round it off to the closest whole number, and that is 2 cycles. Okay, so after 2 cycles the amplitude is reduced to 25%. So this problem is solved. Now let's move to the second problem, and here a damper is offering resistance of 0.08 Newton. Now the damping force F value is given here. Okay, and it is equal to 0.08 Newton, and we know the damping force is equal to C times velocity, and velocity is constant, that is equal to x dot is equal to 0.06 meter per second. So we can calculate the value of damping coefficient from this. C is equal to what? F by x dot, and both values are given. The damper is used with a spring of a stiffness equal to K is equal to 12 Newton per meter. Determine the damping ratio and frequency of the system when the mass of the system, mass is also given 0.3. So it's very easy question. We can very easily calculate the value of Cc first of all. Okay, Cc is equal to 2 root under Km. So this can be done, and C value we have calculated. Let's take the ratio of both. We will get the damping ratio rho. Okay, and then we have to determine the frequency of the system. Frequency of the system omega n is equal to root under Km, K by M. This is the natural frequency, and damped frequency omega d will be equal to omega n into root under 1 minus rho square. So system is actually, if a system is damped system, so system is having frequency equal to omega d. Okay, omega d, and omega d is damped frequency, and this is the frequency with which the system is vibrating now, and this can be obtained with the help of omega n and damping ratio. So this is very easy. Let's go to the third numerical, and in this we have a single degree of freedom system having a mass 2.5 kg with a viscous damping and allowed to oscillate freely. Frequency of oscillation is found to be 20 Hz. So Fd, this is the Fd value. Fd is 20 Hz, and measurement of the amplitude of vibration shows two successive amplitudes to be 6 mm and 5.5 mm. If x1 is 6 mm, x2 is 5.5 mm. Determine the viscous damping coefficient. We have to here determine damping coefficient, Cc value. Okay, so we have already the value of logarithmic decrement here, and delta is equal to ln x1 by x2. Let's calculate this value, and it is equal to 0.087. And for if we take for small values of rho, we know that delta is equal to what? Delta is equal to 2 pi rho. So rho value can be calculated now. If we know the rho value, then we can calculate it C by Cc. Now here viscous damping coefficient was to be calculated, so we are going to calculate here C value basically, not Cc. Cc is the critical damping coefficient. So now we are going to calculate damped natural frequency omega d. Omega d is equal to 2 pi Fd, and Fd is given here as 20 Hz. So omega d is calculated. Now omega d is equal to omega n into root under 1 minus rho square. Omega d we have calculated, rho value we have calculated. What is remaining? Only now only omega n is remaining. So let's calculate it also. Omega n can be calculated as omega d by root under 1 minus rho square. ये भी आ गया. ठीक है, तो हम देख रहे हैं कि for small value of rho omega d is almost equal to omega n. देखिए बहुत ज़्यादा अंतर नहीं है, दोनों के दोनों वैल्यू सेम ही है ना. ये भी 125 है और ये भी 125.6 है. So there is not much difference for a small value of rho. And omega n is equal to root under k by m, and we can calculate here k value is equal to this. Okay, mass was equal to 2.5 kg. Now rho value is calculated, and now only we have to calculate is C. Okay, C can be obtained. C by Cc is equal to rho, and Cc is equal to 2 root under Km is equal to rho. Now in this equation we have already calculated rho, K, and mass is given, so C can be calculated. Okay, and C is equal to 6.41 Newton second per meter. So let's do the fourth numerical, and here we are given a damped free vibration test is conducted to determine the dynamic properties of one-story building of mass m is equal to 10,000 kg. Initial displacement of the building x0 is equal to 0.702 centimeter. Note the unit, it is in centimeter. Maximum displacement on the first cycle is 0.53 centimeter, and period of this displacement cycle is 1.7 second. Okay, and we have to determine almost everything: effective weight, undamped frequency. Undamped frequency means omega n, logarithmic decrement delta, damping ratio rho, damping coefficient c, damped frequency, that means omega d, and the amplitude after 6 cycle, that means x6. Okay, so cycle number is 6 and equal to 6. So let us start with the undamped frequency. Omega n is equal to what? 2 pi by t, because t is equal to 2 pi by omega n. So let's put it, and t is in second, so we will get omega n is equal to 3.695 radian per second, and we know that omega n is equal to root under k by m. Okay, and mass value is given, so we can calculate the value for stiffness. K is equal to 1.3 into 10 to the power 5 Newton per meter, and T can be written as T is equal to 2 pi into root under W by GK. Here W by G is nothing but the mass. Okay, so we can calculate W is equal to what? W is equal to 9.81 into KT square by 4 pi square. But this value will remain almost same. It will come to the same. Either we calculate effective weight directly as mass into G, mg, nothing to do like this, and it will be equal to what? Mass is 10,000 kg into G value is 9.81. So why to do so much calculation like this? Simply follow this value, and it will be equal to 9.81 into 10 to the power 4 Newton. Okay, so we can write it as 98.1 into 10 to the power 3 Newton, which will be equal to 98.1 in kilonewton, almost this value. So this value is also correct, but here effective weight we have to calculate. This is the exact weight. Okay, this is the exact weight, but we have to calculate effective weight. So W effective will be calculated by using this time period only. Okay, and if we put all these values in this W value equation, it is coming as 93.1 kilonewton. So only this much mass, this much weight is participating in vibration here. So effective weight is equal to 93.36 kilonewton, and we are given here that x0 was equal to 0.702 and maximum amplitude x1 was equal to 0.53. It was given. Okay, here it was given that initial displacement of the building x0 is 0.702 centimeter and maximum displacement on the first cycle is 0.53 centimeter. Okay, so we can see that initial displacement was this much, and after one cycle the maximum displacement was this. So displacement is reducing. Okay, so we have to calculate now logarithmic decrement, and logarithmic decrement ln x0 by x1 is equal to delta. So x0 by x1 will be equal to what? E to the power delta. So same thing is done here, and now we can calculate the value by putting all the values here. So delta is coming as 0.28, and delta for a small value of rho is equal to 2 pi rho. So rho value can be calculated here, and rho value is equal to C by Cc. Cc is 2 into root under Km. So here only C is unknown and C can be calculated very easily. Okay, omega d is very easy to calculate, omega n into root under 1 minus rho square. So damped frequency is also calculated here. What will be the value of amplitude after nth cycle? Xn. Xn is what? Xn, we know that Xn by x0 is equal to what? N times delta and ln of x naught by xn is equal to n times delta, because here we are taking natural logarithm of ratio of first amplitude to the nth amplitude. It will be equal to n times logarithmic decrement, n delta. Let's write it in this form: x naught by xn is equal to e to the power n delta. All right, so xn will be equal to x naught by e to the power n delta. So xn can be written as x naught e to the power minus n delta. Okay, since n value is 6 here and x naught is equal to 0.702 and delta is equal to what? It is equal to 0.28. So putting all these value in this equation, now we have got the value for x6 and it is equal to 0.1308 centimeter. All right, so next problem is, an SDOF system is subjected to free vibration with an initial velocity v naught without any initial displacement. So there are two boundary conditions given here, that at time t equal to 0 x naught is also equal to 0 and x velocity naught is also equal to 0. Okay, determine the subsequent motion of the system. We have to determine the equation of motion for the 3 damping ratio. Now rho value equal to 2.5, rho value equal to 1.0 and rho value equal to 0.1. So let's take first of all case 1, when rho value is equal to 2.5 and it is greater than 1. So it's a case of overdamping, and in overdamping there is no vibration, there is no oscillation, there is just exponential decay of the amplitude term. And we have two distinct values for lambda here, lambda 1 and lambda 2, for the solution of characteristic equation, and it will be equal to a e to the power lambda 1 t plus a b e to the power lambda 2 t. Okay, and lambda 1 lambda 2 we have calculated are equal to minus rho plus minus root under rho square minus 1. All right, so let's put this value here into omega n also, and this value will be here written as x is equal to a into e to the power minus rho plus rho square minus 1 omega n t plus b e to the power minus rho square minus 1 omega n t. Okay, and rho value is equal to 2.5 here, and after putting this value we get this equation. Now using the boundary condition given initial condition, when at time t equal to 0 x was equal to 0, and if we put this value t equal to 0, then a plus b comes out to be equal to 0. So a is equal to minus b. Now use the second initial condition, that is at time t equal to 0 x velocity naught is the initial velocity. So let's differentiate this equation, and after differentiation we get this equation: x dot is equal to dx by dt equal to t के जो मल्टीप्लिकेशन में है, ठीक है, पावर में, वो मल्टीप्लाई हो जाएगी सिर्फ दोनों ही टर्म्स में. ठीक है, तो दोनों के टर्म्स में मल्टीप्लाई कर दिया गया है, एंड दिस इज आवर इक्वेशन फॉर वेलोसिटी, एंड पुट दिस वैल्यू हियर t equal to 0. So we get this equation, and here we are putting a equal to minus b. Okay, so this will give us the value of b is equal to this. Now from this value of b we can get the value of a, it is equal to minus b. So we can see the value of a and b just depends on the initial conditions. Okay, initial conditions of the vibration, and the subsequent motion of the system can be written as this value after putting the value for a and b both. Case 2, when rho is equal to 1, so the system is critically damped, and in this also there will be no oscillation, so there will be no any harmonic terms, there will be only exponential decay of amplitude terms, and the lambda 1 value is equal to lambda 2 is equal to minus rho omega n, simply like this. Okay, both of the terms are equal here, and we can put this value here minus rho omega n, sorry. So after putting, it will be equal to what? It is equal to e to the power lambda t a plus bt. Okay, so x is equal to e to the power minus rho omega nt into a plus bt. Now the value for a and b will be again calculated from the initial condition. So put t equal to 0, it will give a equal to 0. Okay, now let us differentiate this equation. X value is equal to e to the power lambda t into a plus bt. Now x dot will be equal to what? So after differentiating, we get this equation. Okay, and if we put here at time t equal to 0, v is v naught. So this will give us the value for b, that is equal to v naught. Putting the value of a and b in the equation, and subsequent motion of the system becomes x is equal to v naught t into e to the power minus omega nt. Okay, now let's take the case 3 when rho is equal to 0.1. This is the damping ratio here, and damping ratio rho is smaller than 1. So we can say that system is underdamped and there will be oscillation. So there will be both two terms here. There will be exponential decay of amplitude and there will be harmonic terms also. So we can see here the first term is the exponential decay of amplitude, that is equal to e to the power minus rho omega nt, and here this value, this will depends on the natural frequency of the system. Okay, whereas the harmonic terms, this is the oscillation term, and this will depend on the damped frequency omega d. So we are you have to note the use of frequency here. In the amplitude it is written omega n, and in the harmonic terms it is written omega d. So system will basically vibrate with the frequency omega d only, and amplitude will decay with the natural frequency. And omega d is equal to omega n into root under 1 minus rho square. Rho value is given, so we can calculate it is equal to 0.995 omega nt. This is by mistake, it is written here t, and let's put this value here in this equation. X is equal to minus 0.1 omega nt into under bracket a cos 0.995 omega nt plus b into sine 0.995 omega nt. So this is clear to us. Now let us put the initial condition at time t equal to 0, x equal to 0. This will give us the value of a equal to 0. Now let us differentiate this equation, and we will get v naught is equal to this. Okay, and a was equal to 0, so b value can be obtained here as 1.005 b naught by omega n. So putting the value of b in the equation of x, we will get the equation, final subsequent equation of motion here. Okay, so this is how we calculate the equation of motions given with the given initial conditions, that is the initial displacement and initial velocity. With the help of damping ratio, we can derive any equation of motion in any situation. And of course we have to categorize in which category, in which characteristic our vibration is lying, whether it is critically damped or underdamped or overdamped. So this is how we do different mathematical formulations on damping and their measurements. So we will be seeing the response in the case of dynamic loadings in the upcoming videos also. So till that, stay tuned and stay safe. Thank you.